Okay, so welcome everyone to another edition of our GEOTOP-A seminar, now in its sixth year. And today it's a pleasure to have Professor Sergei Gukov, who works in mathematics and theoretical physics, and I'm going to give a brief introduction to all of his highlights. And I have to say that he's a pioneer in AI systems applied to topology, and in particular using reinforcement learning to understand questions of profound importance in knot theory. And just very briefly, he is currently the director of the Merkin Center of Pure and Applied Math, and also the consulting director of the American Mathematical Institute, and the John D. MacArthur Professor of Theoretical Physics and Mathematics at the California Institute of Technology. So, with those brief accolades, I want to welcome you, Sergey. And uh, your talk is about a two-variable series for knot complements and recent developments in applications. And thank you very much for accepting this invitation.
Well, thank you for very kind and probably too generous introduction, Pablo. I really appreciate it. And thank you to all organizers for putting this series together, for running it for many years, and yeah, for having me. There will be absolutely no artificial intelligence in this talk. In fact, even natural intelligence will be limited, and most of it is due to my collaborator, Ciprian Manalescu. So this talk will be sort of reflection on the work we did with Ciprian about 5 or by now 6, 7 years ago, maybe, where we introduced a new knot invariant. And you can think of it in many different ways. So the goal of this talk is kind of to look back and describe some of these ways you can think about this new knot invariant. And I wanted to summarize all the key elements already on this first slide. So as the title suggests, it's a two-variable invariance of knots. Equivalently, you can think of them as invariance of knot complements. So this actually will be more useful perspective, perhaps, for many questions. So invariant is going to be denoted by F, and it depends on a choice of knot K. So this part of notation is fairly straightforward. K is a knot. And it will depend on two other variables denoted by X and Q throughout the next entire hour. And Q will be a quantum variable, so we'll talk about quantum groups. And traditionally, quantum invariance and quantum topology are studied at roots of unity, and very little is known about quantum groups at generic Q in terms of corresponding topological invariance. And that's actually going to be the variable Q in this talk. The variable X will be of a very different nature, so that these two variables are very, very asymmetric in terms of conceptual meaning and how invariant depends on these two variables. If you think about either knot or knot complement, then variable X, so I already mentioned what Q is, so variable X will also be a complex variable. It will be continuous generic complex variable. But one can think of it as eigenvalue of SL2C holonomy around the meridian of the knot, along the meridian. So that was sort of the perspective that goes back to 25, 30 years ago. And more recently, in particular in this recent work with Ciprian, what was realized is that this variable actually should better be thought of as a Pentragic dual to spin C structures on three manifolds. In particular, on a knot complement, there is integer worth of spin C structures, and that's this where the label B lives. And X could be viewed as a dummy or generating series type variable that tries to package all integer spin C structures on a knot complement in a single function. So therefore, my advice for the rest of the talk is if you don't like spin C structures or anything spin related, try to think about variable X as just SL2C holonomy, basically. That's probably easier. So there will be gauge connections and some other things around. Or if you do like spin and spin C structures on three manifolds, which actually is very useful for topology, then that's a much better perspective. And as I mentioned here, if you think about X, then it's a holonomy eigenvalue for SL2C connection. And you may ask, why SL2C? What about SLNC or maybe even more general groups? So in fact, most of the talk will be for Lie algebra SL2. So this German G will be SL2 for most of the talk. So I'll talk about quantum group in the most basic, interesting case, non-abelian case. But it's interesting to actually generalize everything that we did with Cyprian to higher rank, and such generalizations are available. So one can talk about SLN, for example, on this side, then it will mean that we'll talk about SLNC connections, and there will be many variables X. So in that case, it won't be two variable series. If you increase the rank, then it will be roughly rank worth of variables X. And also you can replace a knot by link with multiple components. And in that case too, the number of variable X will be multiplied by the number of link component. So the case where we have just two variable series is where we talk about SL2, rank 1, and only one component of K. So it's really a knot and not a more general link. But again, both generalizations are totally okay. Okay, so this is basically the object that we'll be discussing throughout the talk. My goal is to explain why is this interesting, why is this useful. There are zillions of knot invariants. So why do we need one more, and what is it good for? So that's basically the goal. Probably mine and Cyprian's motivation, one of the main items, I mean, there are many ways to motivate it, but many of these motivations end up with some form of categorification. So interesting property of the invariance that we're going to talk about. So in the previous slide, I introduced this object for knot complements, but we'll talk about what it is for general three manifolds, and there will be a constant back and forth between general three manifolds and knot complements. And the crucial property will be that all of this invariance, when expanded as a series in Q, where Q is this quantum variable, will have integer coefficients. And in fact, a conjecture is that this invariant is actually categorifiable. So there is analog of Khovanov homology for three manifolds. It has to be labeled by spin C structures, surprisingly, or maybe not surprisingly. And our hope or goal, main goal in this program is to get closer to this invariance, to the homological invariance, because that would literally be like Khovanov homology for three manifolds. And in fact, some of this work is motivated by physics developments. There will be zero physics in this talk, but just to show that I'm not lying, I here copy what section 6 of a math physics paper with Putrov and Waffa looks like, and it literally says Khovanov homology for three manifolds. So this was indeed where some of these invariants originate. And like I said, I'm not going to spend any time on physics in this talk, but I'll give at least one slide for the following reason. Because the physics picture involves string theory, and string theory is about maps from Riemann surfaces to Calabi-Yaus and other interesting spaces. The benefit of this line of development, or in fact, line of development that goes back to 90s, from which inspiration for this invariant comes, allows to reformulate everything in terms of curve counting. And I'll come back to this a number of times in my talk. For instance, this appearance of spin or spin C structures, which were originally quite mysterious and first showed up in this work with Cyprian, it actually can be understood better and explained from this yet another point of view of curve counting and enumerative geometry. But this is, I'm already picking up speed too fast, so let me slow down and actually now go back to simpler things. So have another 10-15 minutes of sort of introduction or motivation, starting with something fairly basic. As I mentioned, most studied invariants, quantum invariants, and quantum topology live at roots of unity, where Q could be primitive root of unity, as illustrated here, of order K, or more general root of unity. And since we're talking about three manifolds, classical or traditional invariants that now have almost 40-year-old history is set of invariants of Witten-Riccitichien-Turaev, or WRT for short. And the program that involves categorification of not invariants such as John's polynomial, Humphrey polynomial, and many of their variants starts with the fact that you write this polynomial invariant of a knot, for instance. It happens to have integer coefficients. And Sir Michael Atiyeh, a long time ago, back in the 80s, asked, what is the meaning of these integer coefficients? And now we understand that they can be interpreted as graded Euler characteristics of some homology. So it's not really an accident that there are integer coefficients. They actually come as shadows of something much deeper and richer. A natural question is, can we have analog for three manifolds? As I mentioned on the previous slide, what would be analog of Hovanov homology for three manifolds? So counterpart of the Jones polynomial or its cousins is a set of these WRT invariants. And again, the problem is that they're only defined at roots of unity, where Q is something like 2 pi I exponential of 2 pi over K. But the problem is, unlike knot invariants, you can't easily write this objects at roots of unity as polynomials or even power series in Q. So it happened automatically for many knot invariants, but it doesn't happen at all, even for the most basic three manifold invariants. So for instance, here on the slide, I present the answer for what WRT invariant looks like for a particular family of three manifolds. In fact, you can probably guess what it is. It's not so important. But what is important is that if I ask you to write this whole family or lots of expressions as power series in Q or polynomial in Q, it's going to be very hard because, well, the sign of in the sum of pi j over k, that's okay. We can write it in terms of q to the j over 2 minus q to the j minus over 2. But this upper limit of the sum involves a log of q, and so does the prefactor. So if I try to write it in terms of q, it's going to be definitely not a nice power series and definitely not with integer coefficients. So that's the issue. So therefore, back in early days of knot homology theories, when people started thinking about three manifolds, natural question was, okay, can we take these expressions at roots of unity and perhaps find the function of Q such that as Q goes to root of unity, it approaches some of these WRT values. And this was natural thing to expect in Chern-Simons theory. From quantum group points of view, it was already clear that what one needs is quantum groups at generic values of Q. But construction of this function was very ad hoc and often very experimental with no big picture insight. So for example, if your three manifolds is S1 cross S2, so a circle cross a two-sphere, then all WRT invariants at roots of unity are equal to 1. So if I ask you what is the natural function of Q that approaches 1 at every root of unity, you would probably say f equals 1. I mean, that's obviously the simplest, that's obviously the most natural one. However, the invariant that we're going to talk about is not equal to just constant. It's not just 1. It's actually very interesting, a highly non-trivial expression in Q, and we'll get to this much later in the talk. In fact, I'll show you what the answer looks like. But already in early days, it was very clear that just guessing the way I did it is not a good idea. And there were already many hints for this back even 20 years ago, because you can take any function, for example, Dedekind eta function, which will appear later in this talk in a number of ways, happens to vanish at every root of unity. So you can basically add any power with integer coefficients of Dedekind eta, or more generally, you can add cusp forms, and this will not change the behavior at roots of unity, but of course, as a power series in Q, uh, all of these expressions will be very, very different. So this already made it clear that you need some more systematic approach, and that's what this new line of development offers. It offers basically new systematic construction of this function f of Q, such that it extrapolates WRT invariance or values at roots of unity inside the unit disk in the Q plane. Okay. So maybe I'll pause here. If there are any questions, feel free to ask.
It's Renzo here. Sergei, I have a curiosity, a very, very simple thing. Probably the first, second slide you showed, when you mentioned X picking up the role of a holonomy, if you like, is there any connection? I'm thinking of a physical knot, maybe a defect in condensed matter physics. Is there any relation with twist or phases?
Yeah, so
Mm-hmm.
if you think in more physical setup, what I'm describing could be called SL2C Chern-Simons theory, or maybe even more technical proper name would be like a non-perturbative completion of that because of non-compactness of moduli spaces. But yes, one can think there is a physics picture behind where one can view it either in string theory, as I mentioned, or indeed in just purely three-dimensional terms, which would be applicable to some condensed matter systems. So in that case, X could be viewed as part of the gauge connection or some chemical potential or something like that.
Thank you.
Yeah, any other questions? All right, so what I wanted to say next is that based on many of these developments, so this was state of the affairs roughly 20 years ago, 25 years ago, and something that was not expected back then is that instead of a single function f of q, one actually has to have lots of functions for a given three-manifold, all of which are convergent Q series with integer coefficients. And again, their label is either spin C structures, which I mentioned before, or again, if you don't like spin C structures, this set is isomorphic, though not canonically, to the first homology of the three-manifold. So if your manifold is a homology sphere, then we still talk about just one single function. But of course, for general manifold, this could be very large and in fact could be infinite. And as a result, there could be many, many Q series, not just one, for general three manifolds. So in this talk, I'll focus mostly on surgeries on knots. So that's what the title suggests. And in particular, if we have small surgeries or this fractional 1 over r surgeries, then we'll still have just one Q series for this three manifold as a invariant. If we talk about integral surgeries, then there will be as many Q series invariants as this surgery coefficient, integral surgery coefficient. If you have example I mentioned earlier, S1 cross S2, then in fact, first homology of this three manifold is Z integers. So there'll be integers worth of invariants, infinitely many. And if we can consider S1 cross Riemann surface or manifolds with non-trivial Betti numbers, and then there'll be even more. So that was quite a surprise that came with the construction of this FK invariants or their close cousins for three manifolds called Z hat. And that's what I'll try to review in this talk. So the easiest probably way to enter the subject or think about it, or this is one of the ways, is to think about analogy with knot invariants and three-manifold invariants in Reshetikhin-Turaev construction. So this is very beginning of quantum topology going back to 80s and early 90s, where Reshetikhin-Turaev framework could be viewed as a pipeline where one starts in building a three-manifold invariant by representing three-manifold as a surgery or not on an auto link. In our notations, this is denoted by K. Then one studies so-called colored knot or link invariant. So if K is this knot, for example, then you assign colors. In quantum group notations, colors are basically representations of quantum groups, or they can be viewed as Young tableau. So you have to specify something, some representation of your Lie algebra in order to assign this additional information called color to a knot. And in order to produce invariant of a three-manifold, topologically, this operation is the surgery. I'll say a little bit more about it on the next slide. But in terms of constructing invariant, what you would do, you would sum over all possible colors. So you can think about a color as a boundary condition, something like what we call X around the meridian of the knot, or something that labels what kind of additional data this knot is decorated with, or quantum topologists often say colored. So this is the pipeline, and what makes Reshetikhin-Turaev framework easy to work with is that there are two important finiteness conditions. One is that one only considers finite set of colors. So because in the surgery formula, one has to sum over all possible colors, a finite sum is something we love in mathematics. And finite set of colors means a finite set of representations, basically. Moreover, another thing where finiteness plays a very important role is that each color or each representation is actually finite dimensional representation. That's also very crucial in making Reshetikhin-Turaev construction work like a charm without any analytical challenges, is that representations that are used in traditional Reshetikhin-Turaev construction are finite dimensional representations. So even for SL2, as you know, there are finite dimensional representations, and then there are some infinite dimensional representations. And it is finiteness that was really crucial in late 80s, early 90s. And for us, unfortunately, both of these finiteness assumptions or conditions will be totally violated. So that's where the interesting part or delicate part of the story actually lies. In particular, the analog of this pipeline or Reshetikhin-Turaev framework in this modern line of development is that given a knot or, given a knot or more generally link K, one can associate to it a link invariant. I'll focus on knots where there is only one variable X and one variable Q. And then one can construct invariants of three manifolds by performing surgery formula, which just as an old traditional Reshetikhin-Turaev construction is averaging over colors. The only thing is that for us, there will be infinitely many choices. Again, that's where the finiteness condition is gone. And colors are exactly this, labeled by this variable X, which is a complex variable. So averaging or summing over colors will be replaced by integral. So surgery formula will be some form of integral over X, so that X disappears and only variable Q remains, so that resulting invariant of a three-manifold is just a Q series. And that's the Q series with integer coefficients that, as I mentioned before, should be categorifiable and so on. Okay. So as you can see, this construction of three-manifold heavily relies on surgery technique, where the crucial theorem is due to Licorice and Wallace, which says that every connected oriented closed three-manifold can be obtained by a surgery on a link in a three-sphere. And usually when we study surgeries, we first study most general surgeries with rational surgery coefficients. But this theorem of Licorice and Wallace says that you can actually get away with just considering integral surgeries. So sometimes you may have to consider a surgery on a slightly more complicated link, but you can always present every three-manifold as integral surgery. And then there are certain equivalences, some obviously, every three-manifold can be presented as a surgery in infinitely many ways, and these equivalences are sometimes called Kirby moves. So here I give an example that same three-manifold can be obtained either as -1 surgery on trefoil or +1 surgery on figure 8. And in fact, there are infinitely many other links that can produce the same three-manifold with other surgery coefficients. So this is highly non-unique way of constructing three-manifold. So this theorem is fairly well known in three-manifold topology. What's interesting and slightly less known, but will be very useful to us, is analogous theorem here in the bottom of the slide, which says that you can get away, just like here, we reduced rational surgeries to just integral surgeries. You can actually specialize a little bit further and still obtain every three-manifold as a surgery by considering only so-called homogeneous links or homogeneous braid links. So what is a homogeneous link? Homogeneous link is based on a braid presentation. So the question is, can a given link have a braid diagram such that particular generator of the braid group, say sigma 1 or sigma 3, appears either on only positive powers or only negative powers. So for instance, here you see that sigma 1, which represents the first type of crossing, as I read this diagram from left to right, it only appears in a positive power. So I have overcrossing here and also overcrossing here. So this is exactly the homogeneous structure. It could be undercrossing, so it could be going this way, but then everything else where the sigma 1 appears also would have to be undercrossing. So consistency for each given sigma j is what makes braid diagram homogeneous, and by definition a link which has such presentation, such braid diagram, is called homogeneous link or homogeneous braid link. So you can prove this theorem with the technique of Kirby calculus, and homogeneous braid links are actually appearing in various other areas of knot theory and low-dimensional topology. So they were studied by Stallings and others. But for us, they'll be useful in the following way. So modern way of defining this invariance. So the talk is about this two-variable series. So if we consider a Lie algebra SL2 and the quantum group UQ of SL2 a generic value of Q, then claim is that the following trace exists and is well defined, where we consider, just as in Ricci-Tichon-Turaev constructions, nodes colored by representations of the quantum group, but for the representations, and this is the crucial thing, we take infinite dimensional representations. We take so-called Verma modules. So then it's not obvious at all that the sum here, when we take a trace over R matrices where each R matrix is associated to a crossing, would converge. So for example, for SL2, this is how Verma module looks like. Verma module of highest weight. So it starts with some weight lambda, which could be generic complex variable, and then it has infinite tower going either down or up, depending whether we talk about lowest weight or highest weight. So this is similar to classical representations of just classical SL2, say a discrete series, which starts with some either highest or lowest weight. But the important point, it's infinite. So this tower is infinite, and therefore the sums are infinite. As a result, it is one of the important points of this theorem is to make sure that this expression given by infinite sums is actually well defined and gives a Q series with just positive powers of Q or increasing powers of Q. And this was basically one of the important contributions by Sung-Yuk Park from 2021 and nearby years. So he has a series of papers where he developed this approach, and that was followed by other people. Recently, Angus and Laura, so my former and current students, have nice follow-up paper just a couple of months ago on this. And the point here is that the approach is very much in the traditional spirit of quantum topology, where one starts with a quantum group, one associates R metrics to every crossing and constructs invariants of knots and links using just traces over R matrices. But again, the main novelty is that the infinite dimensional representations of quantum groups are used in a non-trivial way. So if you look in details of these papers, you'll see that there is a very non-trivial interplay between topology of knot diagrams and crossings and the highest, lowest weight thermomodules and so on. So that's the definition. That's the definition I want to use in this talk. And as I mentioned, there is a whole series of works by Seung-Wook Park. So in fact, even easier to read paper that talks about a smaller class of knots and links called positive braid knots and links is this beautiful paper where, again, the starting point is quantum group of SL2. And yeah, this is the outline. Many of the things I just mentioned, you can see right here from the start. So review of SL2 and R metrics. And then from R metrics and crossings, he constructs this FK invariant. So it's a very short paper, only 20 pages. So I highly recommend taking a look at it. Okay, so that was the definition. And as a result, what you get is a two variable series in variables X, which again, you can think of as color or choice of infinite dimensional representation of UQSL2, a generic Q. Q is a quantum variable. And what we get is basically this invariant of a knot, or one can think of it as invariant of a knot complement. Thinking about this as a generating function, then B would be interpreted as a spin C structure. Oops. So it turns out, even though original motivation was integrality of coefficients and construction of the corresponding homology theory, it turned out that this two variable series has life of its own, and it has many, many interesting properties that are kind of interesting, curious, or surprising. So starting with maybe less surprising ones, which in fact were expected, is that so now once you have two variables, you can ask what happens if you consider various limits. And there is obviously a lot more to explore compared to what I'm going to tell you, but I'll try to tell you some of the properties where in some of them, the spirit is basically, if you have two variables, let's try to set one variable to 1 or to something else and see what happens. So for example, if you take q to 1, you're still going to get a function of x, and this function of x turns out to be inverse Alexander polynomial. So this was conjectured behavior in our work with Ciprian and Manolescu. And here I want to illustrate how it works for trefoil knot. There is a funny effect that connects Alexander from Alexander polynomial and Dedekind from Dedekind eta function that I already mentioned earlier, that unites them or brings them together. In fact, it's interesting that if you expand Dedekind eta function as a series in Q, you'll get this theta function looking expression where coefficients epsilon m will be basically plus minus ones or zeros. What's interesting is that if you take Alexander polynomial of trefoil and expand this function, basically inverse Alexander polynomial of trefoil knot, you'll get expansion in x and x inverse, but coefficients are going to be exactly the same as for the Dedekind eta function. And I intentionally used variable q for the Dedekind eta function. Well, that's actually traditional in number theory. And here for Alexander polynomial, I used variable x. And if coefficients are the same, natural question is, well, what if we combine them? What if we marry them together? Basically, add x to the m to this expression, or q to the m squared over 24 to the inverse Alexander polynomial. And if you do that, what you get is exactly the inverse, exactly the two variable series for trefoil knot. So that's going to be concrete example. That's how it looks like. And as you see, it has integer powers, integer coefficients, so all good. So what I described here is a limit of this object that we introduced as q goes to 1. But then you can do many other things. For example, if you ask what happens at other roots of unity, you recover so-called non-semi-simple or logarithmic invariants of knots originally introduced by Akutsu, Deguchi, and Otsky. So these are polynomial invariants kind of similar to Alexander polynomial, but they're also labeled by choice of root of unity. And if you take radial limits in variable q to other roots of unity other than q equals 1, you'll find this ADO polynomial invariance. You can also expand near q equals 1, for example, write as q as exponential of something small, and then you'll discover Vasiliev invariance. And another thing which was in fact expected, not surprising at all, is that this two variable series obeys recursion relation, which comes from quantization of a polynomial. So a polynomial is yet another knot invariant. So there are many, many connections. And some of them, for example, this limit where q is near 1, I just mentioned relation to Vasiliev invariance, can be expected, and in fact was expected, from developments in mid-90s, late 90s, and connection to this enumerative invariance, which I mentioned before, where there was a very similar connection between so-called Gromov-Witten enumerative invariance and Donaldson-Thomas enumerative invariance. So people from late 90s and early 2000s observed that Gromov-Witten invariants are not integers, but and they're hard to compute, or sometimes hard to see certain structures in them. But again, integrality is the main property I care about here. But if you exponentiate this generating series of Gromov-Witten invariants and re-expand it in a new variable q, which is exponential of the previous variable, then the coefficients will be integers, and these are precisely the Donaldson-Thomas invariants. So from the viewpoint of q series, this object has natural expansion near q equals 0, because when we write it as sum over coefficients and then q to the n, we assume that each next power of q to the n is smaller, so we're expanding near q equals 0, whereas this expression naturally leaves near q equals 1, where this variable here denoted by h bar goes to 0. And so q is near 1. So basically, these two are related by re-expansions in very different domains, one near 0, one near q equals 1. And the story that I just told you about, where we saw a very similar relation between this two variable series that we introduced with Chyprian and, for example, the packaging of Vasiliev invariance near q equals 1, is actually not a different story. It's precisely incarnation of this much more general story through this connection to enumerative geometry that I mentioned in the very beginning of the talk. All right, so I'll conclude with going over various other properties that might be interesting to people. So I mentioned in the beginning that spin C structures appeared in this story as a sort of surprise, and indeed they were quite unexpected, at least at first. But then there were many works in recent years which shed light on spin C structures and connected these new invariants to other invariants of knots and three manifolds where spin C structures appear naturally. And in fact, large class of them has to do with Higart-Floer homology, where, again, invariants of three manifolds are also labeled by spin C structures. So there was a very nice series of works by Ahmedshad, Johnson, Krushkel, and then Ahmedshad, Johnson, and same Park I mentioned before, where they studied connection between invariants I'm talking about in this talk, and a particular version of Higgs-Floer homology called lattice homology introduced by Andros Nemethy, which is very combinatorial and very easy to work with. And they did several things. So first of all, they connected ingredients which are maybe more representation theoretic, such as what I told you about in this talk, to graded roots and other elements of Nemethy's construction in this lattice homology. So those of you who have worked or seen lattice homology or Higgs-Floer homology can probably recognize some of these diagrams. But also they managed to generalize the set of invariants to a much larger universe, sort of placing them in a bigger family and shedding more conceptual lights on other ingredients, not just spin C structures, which was quite important at the time. So other works in related but slightly different spirit were by Moore and Taraska, where they looked at what happens for high rank and made very similar important contributions. Recently, there was work of Andros Nemethy, whose name I mentioned just a moment ago, with Shemal Harichurin and Joseph Svoboda, where they try to focus on the leading powers in Q of these Q expansions, and there is some interesting interplay between this fractional powers and correction terms of Higgs-Floer homology. So again, yet another link to Higgs-Floer homology. And there have been many other properties of this new invariant studied as a Q series. So you can ask if they have interesting modularity properties and so on. And again, that's yet another angle you can look at in this domain. So another class of properties could be organized by asking, is there a TQFT structure? So in quantum topology, every time you construct invariants of knots and free manifolds, and in this talk, I try to construct this invariants Fk and Z head. So you can ask, can they be unified in some TQFT? And the answer is I don't know, but I can give you preliminary answers or what they or say something about work of mostly other people about trying to define this TQFT for a two-sphere and a two-torus. It would be important to extend this to surface of any genus, which we currently don't have, but at least for two-sphere and two-torus, I can say something. And these are some of the most important ingredients in TQFT because the vector space that one associates to a two-sphere should be commutative ring, and sometimes this could be viewed as ring of functions on a certain space. And what one associates to a two-torus could be viewed as a Grothendieck group of Hochschild homology of some category. And this is important for various categorical developments. And here I want to highlight work of Mrunmayee Jagdale, who tried to study these properties. In particular, for a long time, it was expected that space for the two-torus should be just this, which is, so the answer written here is essentially quantization of space of complex SL and C, or in our case, SL2C flat connections on a two-torus. And there was no reason to expect that this needs to be modified or changed. But recent work shows that in this TQFT, if it exists, the space would be actually larger. Part of the reason maybe is easy to spot, that we already talked about spin C structures, and this space would not take the spin C structures into account. So that's maybe one reason. But like I say, this subject is not so well understood, in particular because in higher genus, we don't know what the answer should look like, and that would be one interesting direction to pursue. Another reason, this work of Mrunmayee, in fact, he has recent paper which either came out or is coming out where there is more on the subject, is because this space, which is quantization of character variety of the torus, has interesting connections with spherical Daha, and that was actually expected because you need mapping class group of a two torus to act in a natural way, and for two torus that's SL2Z, which is precisely the SL2Z symmetry of Daha. But again, because this character variety is non-compact, this non-compactness is basically manifestation of infinite dimensional representations that we encountered in the very beginning. Morunmei argues that this space of a two torus should be actually much larger than expected, and potentially instead of spherical Daha, one needs a different algebra, which I'm not sure is studied in algebra literature. So this is yet another interesting direction. One more comes from our work with Hirako Nakajima, Po-Sheng Singh, Sang-Yuk Park, Dupay, and Nikita Sepenka, where we connected the subject to Rozansky-Witten TQFT. So this is yet another sort of area one can consider working on. But just like in representation theory, the interesting part was replacing finite dimensional representations by infinite dimensional representations. Here, the interesting part of this TQFT that we talked about in this talk is that unlike the usual applications of Rozansky-Witten TQFT, one needs to take infinite dimensional target spaces. So in particular here, based on affine Grassmannian. And earlier in the talk, I promised you the answer for S1 cross S2. So naive answer would have been just +1. But as you can see here, the answer is highly non-trivial, and it's definitely not +1. We can talk more about it, but again, here I just wanted to show that it's not as simple as one could think. And interesting aspect of this theory is that it's mathematically well defined. So Kontsevich and independently Kapranov had definitions, mathematically rigorous definitions of Rozansky-Witten invariance and Rozansky-Witten theory. So again, the only difficult or interesting part here is that one wants to apply it to infinite dimensional target spaces. And again, this is manifestation of infinite dimensional representations we saw before. And finally, something very recent in work with Pavel Putrov just a year ago, we showed that indeed one can lift this invariance I talked about on this talk to homology theory. So in other words, this categorification dream or program that was original motivation can be realized at least for plumbed three manifolds. And this categorification is, at least in our approach, is based on Fukaya-Seidel category associated to complements of hyperplanes in some symplectic space. So important property is that it's invariant under Kirby move, so that guarantees topological invariance. And what we learned in this work is that the non-compactness of various spaces that I mentioned just briefly or in passing throughout this talk is actually very important. So when everything is finite, when everything is compact, there is no problem. But if we have integrals over complex variables which take values in non-compact domains, it's important to ask what are the compactification divisors. So if we have some moduli space, for example, what would be the information at infinity that we need to provide in order to make this, say, integrals of various quantities, characteristic classes well defined. And what happens here is by now it's becoming better and better understood, in particular in this same paper with Pavel Putrov from a year ago, we emphasize that there are important contributions of these compactification divisors, which sometimes contribute in additional saddle points or contributions that you wouldn't expect. And that's why here in this talk, I call them black swans, because again, naively, you wouldn't expect them. But of course, once you see them, it's not too surprising. And that's yet another kind of area or sort of questions that I think would be interesting to study further. So here in this last slide, I basically summarize all kinds of questions where I include this question about black swans, but there are many other things that one could study. For instance, in this work with Cipri and Manolescu, we studied surgery formula for non-zero surgery coefficients, but in many ways, zero surgeries are the most interesting ones. In the work on categorification that was toward the end of the talk, we developed it with mod 2 coefficients. So I think it would be interesting to extend this to homology of three manifolds with integer coefficients. So then another obvious question is, how does this homology behave under homology cobordisms and so on and so forth? So there are many questions, and maybe one big punchline here is that even though the subject has good momentum and has been going on for several years now, there is definitely a lot more to ask than to be able to answer. So thank you for your attention.
Well, thank you so much, Sergey. That was so much information, so many directions. If everyone would like to join me in thanking Sergey, if you want to unmute your mic and clap or just say hi, you're welcome to. And so would anyone have a question right now for Sergey?
Actually, I have a curiosity, Sergey. Actually, two questions, if I may. One is very basic, and maybe you want to talk about this later, or whatever. One is about curve counting and Betty holes, etc. If you can provide some comments on that. You mentioned that at the beginning of your talk. The second thing is that second question is I was really surprised to see the combination of the Dedekind expansion, series expansion, and the Alexander polynomial when you mentioned the case of the trefoil knot. Is that a particular case, or you can do the same with other type of knots and links? Because this series combining these two contributions is quite amazing. That's all.
Yeah, thank you for both questions. Indeed, I don't think Alexander and Dedekind probably didn't know much about trefoil knot. That would be my guess. And I don't know if Alexander knew that if he takes his Alexander polynomial and expands the inverse of it, he would get anything related to number theory. But that's basically the style of these two invariants. They tend to combine some number theoretic or maybe modular-ish object, which depends on Q, and indeed fairly clear topological invariant, such as Alexander polynomial, or again, maybe this ADO invariance. So the answer to your second question is, I view this as a coincidence, kind of, but maybe there is something much deeper if one tries to look at other knots and links. For example, torus knots would be natural candidate because
Indeed.
trefoil knot is beginning of the sequence of 2 comma p torus knots. So maybe studying this sequence first, one can one can generalize this property. And yeah, that's where I would go. Regarding the first question and curve counting, so this is a very rich story, and I would highly recommend several recent works of Tobias Ekholm and collaborators. I think I mentioned some of them in some of the slides. Let me try to see if I can find references. In fact, Tobias and some of our friends and colleagues, including myself, had various papers recently on this. And this is a very rich story which connects two areas of mathematics, and it is these interconnections between areas of math which excite me most. So here my talk was mostly about quantum topology, but I tried to mention this connection to enumerative geometry, and that happens in the world of Calabi-Yau manifolds and Lagrangian submanifolds. And one is studying pseudo-holomorphic curves in Calabi-Yaus, maybe sometimes with boundaries on Lagrangians. And that is very different subject in a sense that it doesn't talk about quantum groups, it talks about geometry. And to me, it's really amazing that such highly non-trivial objects, these invariants that we talked about, they can have life and meaning without any simplification in both worlds. So on the one hand, they can be viewed as this quantum group invariants for quantum groups at generic Q, but on the other hand, they represent this curve counting and Calabi-Yaus. And again, Tobias would be the right person, or he has done a lot of work in recent years, which of course rests on many other papers, such as the ones I mentioned here. But in one of his papers, for instance, I forget what the second author, it's a two-author paper, they talk about Alexander polynomial, and that could be curve counting explanation of your second question, for example, relation to Alexander polynomial. So yeah, this story with curve counting is amazingly rich and interesting.
Thank you very much. I'm amazed myself by the ramification of what you presented in so many different areas of mathematics. Thank you.
Thank you.
Does anyone else have a question that they would like to ask right now? Well, maybe while you think, I have a kind of a speculative question in a very similar direction to what you were just talking about, because maybe if you go back to this slide with the Donaldson-Thomas and Gromov-Witten. So I guess we, there's also the Sibberg-Witten and Gromov-Witten equivalences that Taubes showed. And that those are, I guess, should be easier than the Donaldson-Thomas because they're just dimension 4. But there's also related to these Fukaya-Seidel categories, there's a conjecture by Seidel and Smith of an equivalence between Kovanov homology and Floer homology. So I guess that would be a different direction to see this bridge between the curve counting and the Kovanov homology directly. Although I haven't kept up to speed of what the state of that conjecture is, but I mean, do you see other directions going towards Floer homology? Because you mentioned Heggard-Floer homology as well, but that would be a different one.
That's right. And all of these are indeed not unrelated at all. So indeed, one can think of relation for symplectic manifolds. So Taubes proved this beautiful theorem that Seiberg-Witten equals Gromov. And that fits really well with this framework. But then, as you correctly point out, there is indeed, in fact, there are many works on symplectic and Fukaya-Seidel type definition of Khovanov homology. And actually so here I was very brief about what we do with Pavel. So we construct some Fukaya-Seidel category. And actually that's highly motivated and not very different from what one sees in Heggard-Floer. So you're absolutely right that all of the subjects, Heggard-Floer homology, sort of Fukaya-Seidel, and various other symplectic definitions of Khovanov homology, and the one here on the slide, they are not too unrelated. They all share many different many properties in different corners, and yeah.
Well, thanks. Yeah, this is very fascinating. Does anyone else have another question that they would like to pose now?
So maybe as people are thinking, I can make another comment on your question, which is really, I mean, it's yeah, this analogy and thinking about all of them together is a good idea, because here what we did with Pavel is did it for closed manifolds of a certain type called plumb manifolds. But an actual question is to ask, what about categorification of this two variable series for knots or knot complements? And this has not been done. And I think since you mentioned this work of Seidel, Smith, and others, that's what would be the right motivation or starting point for trying to do something similar for FK, namely categorifying this FK invariant. So, which is yet another problem I didn't mention here.
Yeah, that's a fascinating direction. I think those papers that you mentioned, I consider them to be very technical and hard, but it's definitely something worth developing. And yeah, understanding these how these curve counting ideas fit in, and how these Lagrangian spaces of Fukaya categories appear, that would be fascinating. Several people have opened up their videos. Do you want to ask a question now, or please go ahead? Maybe I'll ask another question that is just curious. Since some of these actual computations that you showed us sometimes appear more as number theoretical expressions, to what extent have you found in researching these directions that you end up at points where you get to parts that are not known either in number theory? I mean, does this just kind of, does it happen that you retranslate it into something that is very difficult in that area, or that you find solutions in that area? Yeah, thanks. I think that because I don't, this is something that I don't really know much about, to be honest.
Yeah, so here I mentioned briefly two works, but in fact, even within these groups, they have many series of papers, Catherine Brinkman and her team, and also young team of Louisa Lils and Eleanor McSpirit. So they have other papers as well. And what's interesting and exciting, I already mentioned that to me personally, throughout my entire career, but also in this line of development as well, is the bridges between different subjects. And very much like the bridge to enumerative geometry is what makes it exciting is that it translates something at the cutting edge or meaningful or worth studying in quantum topology to something of equal difficulty or complexity in curve counting. And the same here with number theory. So indeed, if you look at all this invariance and ask, okay, what kind of number theoretic properties they have, this leads to some of the coolest things that are happening in number theory right now. So it provides a bridge where level of excitement or complexity is equally high on both sides. So in some sense, maybe that's not a great thing. It would be maybe nicer if we could translate something hard on one side to something well understood on the other side. But it actually doesn't happen. And I view this as a good thing because it means that it is actually contributing in a meaningful way to development in the other area. Yeah.
Yeah, thanks. That's very interesting. I mean, it sounds like there's so much work in so many directions. Yeah.